earth science classes, including geology, climatology, and earth history for more than 18 years. Nicole brings her enthusiasm to the community by offering earth science field explorations and presentations. She has taught at Sonoma State University, College of Marin, and Santa Rosa Junior College, and offers community classes through her business. Now, I just lost my screen there. Nicole Myers, you can fill that in.
Yes. Appreciating Earth.
Appreciating her. Thank you.
Absolutely.
All right.
Thank you for that intro.
Cool. So it's all yours, Nicole.
Well, thank you. Thank you so much for having me. For those who know me, because I definitely recognize quite a few names on the list, you know that I'm not great at identifying plants, but I can tell you about the rocks in the soil. I love when I have plant people come on my trips because then you can tell me what the plants are called. I call them all pretty, but the rocks are definitely what I have my knowledge base on. So my intent is to talk about the geologic history of the San Francisco Bay region with a little more focus towards the North Bay, but quite a bit of the information is more like regional, zoom out regional. And what I hope that I can get across is that the geologic history is what determines which rocks are close to the surface. And all of our rocks have unique chemistry, and that chemistry is going to play a strong role in the formation of soil, which, of course, as you all know, is going to determine which plants can thrive in any one area. And if we zoom in on geologic time of our more recent time, we can see how climate change of really even the last few million years has played a pretty strong role in creating the landscape as we know it today. And determining which ecosystems have been able to survive. So a lot of the more rare plants and rare soils are kind of islands of ecosystems that are the remains of that which has shrunk since the last time there was a lot more ice on Earth during the last glacial stage. So again, I'm Nicole Myers, and I wanted to just point out a couple pictures here to start with. So here in the middle, put a check mark on it. We have our terrain, and right down here, here's Tomales Bay. This is the San Andreas Fault, or at least close enough as far as my ability to draw a straight line with a marker. And the San Andreas is a dividing point because a lot of movement has taken place on that fault, causing the rocks on the west to have a different geological history than the rocks on the east. And over here to the left, a picture supplied by your organization and taken by Woody Elliott is a picture of McClure's Beach, which is right about there on Point Reyes. And the rocks, the sandstone that you're looking at in that picture is very largely going to be the result of granite rock from the Sierra Nevadas that's broken down into small sandy pieces that became the beaches of the past and the bluffs of the present. And yet these rocks of Point Reyes, and therefore the soils of Point Reyes, have a very different history than the rocks and soils that are east of the San Andreas. But the rocks both west and east of the San Andreas, all the way to the western edge of the Great Valley, are part of the California geomorphic province called the Coastal Ranges. And the San Andreas fault is just one huge fault among many hundreds, really thousands, millions of faults that make up the San Andreas fault system, which is going to be a pretty important part of the description of the geologic history of this area. So zooming in on the North Bay a little bit, here on the upper right part of the screen is a geologic surface map. So each one of those colors is a rock with a unique origin story. So how did it form? When did it form? Where did it form? A lot of it formed in the ocean. Those are marine rocks. And some of it formed relatively recently, and many of those rocks formed many tens of millions, if not hundreds of millions of years ago. And my hope was by putting up this map, you're like, oh, there's a lot of rocks. And that you can see the pattern of the black lines are faults. But you can also see some of the colors kind of follow this northwest southeast trend. And those are the faults of the San Andreas fault system. This big red one here, that's the San Andreas proper, which is just a main fault within the system. There are only three rock types, which we will soon see: igneous, sedimentary, and metamorphic, but all three rock types are present in our region. And part of that is just the complexity of the geology here. So to kind of take care of some of that complexity, we tend to take groups of rocks and put them into groups or formations in order to simplify. So here on the left side,
Which gave
all of the pink stuff, those are volcanic rocks that erupted relatively recent time. I'll put that in a timeline here during the course of this next hour. And then all of these kind of yellowy, orangey rocks through here, those are actually rocks. Let me specify rocks west of that line. Those are rocks that formed in a shallow ocean in relatively recent times. And you can see they're adjacent to these gray rocks, which also formed in the ocean, but much longer ago, like up to 200 million years ago and closer to the equator. So we have this huge span of time, but we also have a huge variety of rocks. So here's the San Andreas. And I just want to point out a couple of the other big ones. Here's our Healdsburg Fault, Rogers Creek Fault, which is part of the Hayward Fault system. Here's the West Napa Fault. Here's Burdell Mountain Fault. I'll talk about that here in the near future too, because that's important to the Marin area. What I hope is that you can see the relationship between the topography, the northwest, southeast trending valleys and mountains, and the rocks. And we can also see that there's a great variety of rocks, which will lead to a great variety of soils. But when it comes to the west coast of California, it's geochaos. I feel really bad for students who have to learn geology here because it's as complicated as it gets. So we tend to try the simplification. Here on the left, we have a terrain map, and it's TERRANES, and terranes are basically just group the rocks into common origin. Which environment did they form in? So in these areas that are just white, this is what we call cover terrain. I'm going to come back to that closer to the end because that's the rock stuff that's on the surface. And we can see that shown here in this cross section. Some of it's this orange stuff that's volcanic. Some of it's got the like big dots that's relatively recent rocks. Some of it's relatively old rocks and teal, but those rocks that are kind of acting like a frosting atop the older rocks, those are cover rocks. And they are largely covering up or on top of, which I have highlighted in blue, these rocks with the diagonal lines from top left to bottom right, oceanic terrain. That's what all this teal stuff is in the bottom right. That's all Franciscan complex. And they use the word complex because it's so complex that geologists get angry with each other and literally have fights over whether or not the word formation can even be used. Essentially, it's a whole group of formations. It has a very complex history. There's a lot of different kinds of rocks. And if we zoom into Sonoma County and Marin County as well, we can see that it's kind of a compilation or a patchwork of this oceanic rock, much of it very old, some of it relatively recent, and the cover rocks on top of it, which are mostly volcanic rocks and some river deposited rocks. But if you have a different rock on the surface, it will form a specific kind of soil, which will then, of course, form a specific ecosystem and therefore different plants. So we have our three rock types: igneous, like ignite, as in to ignite flame. That's our volcanic rocks. And in California, we have a couple main groups of our volcanic rocks. Here in this kind of salmon colored pink, those are granitic rocks from the Mesozoic era. So the time of the dinosaurs between about 252 to 66 million years ago. That's Mesozoic. The areas that we see in pink were deep. We're talking well over 10 miles below the surface, and they were giant magma chambers that were being filled with magma rising from below. And then that magma would erupt and form these large volcanoes. So we have these volcanoes that would have formed along what was then closer to the coastline. But those volcanoes are all done erupting. And now the magma chambers, which are cooled and solidified into granite, those magma chambers have been faulted, uplifted to the surface. And yet notice that we have some of that salmon color right there at Point Reyes and Bodega Head, because some of those granitic rocks, those magma chamber rocks, have been faulted to their current location. You can blame the San Andreas for that. We have some other volcanic rocks that are important. For example, in this orangey color, those are the Sonoma volcanics. They're tertiary, so relatively recent. Recent is at the top of the geologic timescale here on the right side of the screen. So you can see in millions of years, MA is for millions. Recent's at the top and old's at the bottom. So the tertiary rocks are recent volcanic eruptions, and those are going to include Mount Burdell. So we're going to have some of those rocks that have formed really within less than the last 20 million years. Then we have our sedimentary rocks, and our sedimentary rocks are rocks that form on the surface of the earth. They're so important for climate change. When we are looking for records of how the climate has changed on the surface of the earth, sedimentary rocks are the record of climate change. They form in specific environments, and therefore they are recording the environment they formed in. And we can see we have a lot of green. That bright green, those are Mesozoic, time of the dinosaurs. Most of that is sedimentary rock that formed on the ocean floor, long before that rock became part of California. We also have some of these gray colors, which are relatively recent, again, tertiary for recent, relatively recent sedimentary rocks, some of which are oceanic, and some of which were formed more by the process of river erosion. And you can also see the yellow. The yellow is also our sedimentary rock. And the last of our three rock types is metamorphic. And I love metamorphic. I'm partial to volcanic rocks because volcanoes are the best thing ever. But metamorphic rocks, they're so sparkly. And if you go to Ring Mountain, you have certainly seen fantastic metamorphic rocks. The vast majority of metamorphic rocks form at great depth. And we can see the purpley areas, the darker purple blue areas. Those are older metamorphic rocks. And there are some of those metamorphic rocks also kind of tucked inside of those granitic salmon colored rocks, which we will soon see. So all of our rocks are going to belong in one of those categories. And the rocks themselves record Earth history. It's going to record how the surface of the Earth has moved, where the volcanoes have been erupting, where were there mountains, where were there valleys. The process of movement is what we call plate tectonics. And just like there's three rock types, there's three ways that the edges of plates, the surface of the Earth, the three ways they move. So you can have two plates pull apart from each other, diverge, and that's a divergent boundary. You can have two plates come together, one's going down, and as a result, you have a convergent boundary. And then we have transform, which is more or less sliding side by side, less vertical motion, more horizontal. And that's like the San Andreas Fault. And we will see how all three of those tectonic boundaries have created California as we know it. And in our region, we have all three rock types present. That's actually fairly rare and awesome. But as a result of the complexity of the rocks and the tectonics, we have a very complex landscape. And the formation of the landscape is what determines which soil is going to form on the surface, which again determines which plants can survive. Our coastline, if I'm going to hyper simplify it, is very largely made out of marine or ocean sediments, chunks of ocean plate itself, and the rocks of magma chambers, and even the material that has erupted out of those volcanoes. So we live on North America. I assume you knew that. We're on North America. It is both a continent and it's also the name we give to the plate. You can see our continent's more in the gray color, whereas the plate extends kind of not entirely within the boundaries of the continent. Here's the eastern boundary in the middle of the Atlantic Ocean. And our San Andreas Fault is the western boundary of North America. I'm going to get to this little guy here. Juan de Fuca is a tiny little plate. It's an oceanic plate that is to the north of us. It goes from Cape Mendocino just up into BC, Canada. And what makes Juan de Fuca amazing, excuse me, is that it is a tiny remnant of the Farallon plate. So here in this map on the right, this is showing today, 0 million years ago. And here on the left, this is showing 190 million years ago. So more or less during the time when like some of the really big long neck dinosaurs were walking around. Pangea had just started to break up at this point. And the Pacific Ocean, as we know it, was huge. So here we have the Farallon plate. The only pieces of the Farallon plate that still exist today are the Juan de Fuca and the Cocos plate. Everything else has subducted at convergent boundaries. And look at this little teeny tiny blue triangle. That's the Pacific plate, the baby Pacific plate 190 million years ago. And today the Pacific plate is huge. We can see that it is the majority of the Pacific Ocean. And around the edge of it, much of it we call the Ring of Fire. That means the Pacific plate has grown over time at divergent boundaries, while the Farallon plate has shrunk because it's been sinking down or subducting at a convergent boundary. If we start to focus on the west side of North America, we see that the rocks are formed by volcanic eruptions due to that convergent boundary, one plate going down. But those convergent boundaries don't just create the volcanoes. If we imagine my arm here is all of that sediment, that muck that's on the top of the oceanic plate. When it's going down, that sediment's going to get scraped off onto the adjacent plate. And that's what most of our coastline is made out of. That Franciscan complex, that's just the rocks that got scraped off onto North America. So in addition to having those rocks that we call accreted terranes accreted onto, added onto North America and the volcanic rocks from the eruptions, we will see in a few slides that the Pacific plate in our modern day has added some more complexity to the picture. I'm going to get to that with pictures in a few slides. But I have this video playing in the upper right corner without sound. And as it's speeding up the process, but it's showing us a divergent boundary, two plates, oceanic plates pulling apart from each other. And then now a convergent boundary where the ocean plate dives relative to the adjacent plate. And as it dives, we will soon see that there are volcanoes that are erupting. Remember the Sierra Nevadas, all that granitic rock, those magma chamber rocks, that's how that magma ended up there. Is you had the Farallon plate going down underneath the North American plate. As the Farallon plate was subducting, it would get hot as it got closer to the core, melt, the magma would rise, and then that magma, as it punched up through North America, would form volcanoes. And those volcanoes, the magma chambers from those volcanoes have since been faulted to the surface, and we call them the Sierra Nevada mountains. So the story of our coastline tectonically really is the story of the Farallon plate and the Pacific plate. Both of these plates are mostly oceanic crust. All oceanic crust forms at divergent boundaries. And the oceanic crust gets subducted at convergent boundaries, fueling volcanoes, but also squishing rock onto the edge of the continents. The West North American plate is largely continental crust. So we have oceanic crust and we have continental crust. The oceanic crust is denser and heavier. That's why it can sink down. Whereas the continental crust is a little bit more buoyant, less dense. It can't subduct, so it becomes the land that you and I live on. But that means for continents to grow, to get bigger, you have to have material being added onto the edges and erupted up through it. And convergent boundaries are largely the reason that takes place. It's the reason our continents grow. So here, if we go back to 180 million years ago, we have the Pacific plate. So think of this is our divergent boundary. Here's the Pacific plate. You have new ocean crust being made there. Then you have the Farallon plate, also oceanic, but it's going to head eastward until it encounters North America, here, our continent, and you have the subduction of the Farallon plate underneath North America, creating the Sierra Nevada volcanoes. And here on the right, we get a pretty good image of that. This is during the time of the dinosaurs, like the last half of the dinosaurs for the most part. Remember the Franciscan complex? This is all in blue, all of that stuff that's been scraped off the top of the plate. Sometimes that includes islands, islands of long ago. It includes the fossils of marine organisms and all of those ingredients that were once on the ocean floor, whether they were alive or just part of the rock world. Those are going to become the ingredients that will go into the formation of soil. So when it comes to serpentine, which is of course a hot topic among anyone who loves their plants, serpentine as a group of minerals that makes up rocks, it forms largely at divergent boundaries. I'm on the left side of the screen where hot water is being flushed through faults. But that serpentine can also form at convergent boundaries and is the result of, again, heated water moving through rocks. And that heated water essentially is baking the rocks and forming the serpentine. So we have these pockets of serpentine in our region because of this old subduction zone. Over here and back on the right, we have the Sierra Nevadas. Here's those magma chambers. We know those are going to have to be uplifted to become the mountains of today. We know by studying the rocks that the Franciscan complex is largely between 140 to 40 million years old. And we call it an accretionary wedge because it's a wedge shape. An accretionary, because to accrete means to take many small things and add them together to make something bigger. So every time you clean the lint out of your laundry, out of your dryer, you're accreting a ball of lint. So it's a wedge shape accretion of material. This, you can see, is below the ocean during the time of the dinosaurs. It too must be uplifted to be above sea level because you and I live on it. There's also chunks of oceanic crust that get stuck in it and become part of our region. And some of those rocks, they went down and they got baked into metamorphic rocks. And when you go to Ring Mountain, quite a few of those rocks are metamorphic and they got brought to depth. We also, evidence of this Farallon subduction, have the Salinian block. So Franciscan complex, Salinian block is just another name for a group of rocks. Those are these magma chambers that have since cooled into the granitic rocks and are now the Sierra Nevadas. And some of those rocks have made it all the way to Bodega Head and Point Reyes as a result of faulting. And those rocks, those magma chambers largely cooled between 125 to 85 million years ago. So you can think of that as the time when the volcanoes were actively erupting. So those Salinian blocks are interesting because that is one of the reasons for those of you who've been on Point Reyes that if you're at Tomales Bay, the vegetation to the west on Point Reyes looks very different than the vegetation on the east side of Tomales Bay. Because on the east side, you have the Franciscan Formation, the ocean muck, the accretionary wedge. On the west side, you have the granitic rocks that were once magma chambers at depth. Totally different rocks, totally different origins, completely different chemistry, therefore different soil. So if I focus on those Salinian block rocks, they are just pieces of the Sierra Nevada that have been displaced by faults. So in the bottom right, in orange, you have the granitic rocks that formed in those magma chambers. They are the cooled magma chambers. And everything that you're seeing in this kind of green and red color, this is what we call the Salinian block or the Salinian terrane. It's literally pieces of rock that started over here in the circle I just drew in the bottom right and have since been faulted westward and then northwestward by the San Andreas fault system, literally dragging chunks of southeast California all the way up to become our coastline today. The Salinian block rocks, those specifically granitic rocks, are the 125 to 85 million year old rocks. The actual magma chambers would have cooled at around 25 to 40 kilometers deep. Think of minerals like quartz and feldspar. You're going to get some of our darker colored minerals as well, but I'm on the upper left, and you can see what some of these rocks are going to look like. They formed inside the earth, intrusive, and they have big minerals. So this is going to break down into a very, very different kind of soil than, say, ocean mud would. But within it, and I'm here in the center now, this is that granodiorite or granitic rock. Notice those darker chunks in there. Those are what we call the Sur series group. That is the rock that pre-existed the magma chambers, because the magma had to intrude into whatever was already there. It had to be there first. So we're not surprised that these rocks are older, 360 to about 280 million years old. I'm in the bottom left. They're essentially going to be the rocks in this green color that the magma intruded into, and that magma baked those pre-existing rocks, which originally came from the ocean. They are originally marine sediments, baked them. Pieces of the rock fell into the magma chamber where those marine sediments became the metamorphic rocks that we call the Sur series. And so you will actually see slightly different soils when there's more Sur series present, because it provides different ingredients to create a different soil. So if we look at the Sur series, I'm going to the bottom, it essentially would have been the sediments that formed in this area before the dinosaurs even existed. And then later, the magma came in and baked it. And then later, faults came in and uplifted and moved those rocks to where we see them today. But obviously, to get from that subduction zone, that convergent boundary of the Farallon plate going underneath the North American plate to the landscape of today, some massive transition had to take place. And it did. Because today we do not, where we are, we do not have a convergent boundary anymore. We have a transform boundary. I'm going to head to the bottom left part of here. There's the San Francisco Bay. And this pink area, I'll get to here shortly, but I'm just tracing the San Andreas. Here we have the Cape Mendocino, which is where the San Andreas fault system ends. The San Andreas kind of leaves land and goes into the ocean closer to Point Arena. And north of Cape Mendocino, notice here's our divergent boundary, forming new oceanic crust. This is the Juan de Fuca, and it's going underneath North America. And we still have our volcanoes, aka the Cascades, that are erupting to our north. So this is our modern day tectonic setting. Notice down here we have the Cocos plate. It's that other remnant of the Farallon. So in this lime green color, those are the last bits of the Farallon that are still actively subducting and will someday go away. But remember, the Farallon was huge. It was most of the Pacific Ocean. Therefore, everything between the Juan de Fuca here and the Cocos here, this all once was the Farallon plate, but it has fully and completely subducted beneath North America. So we'll go to 60 million years ago. The star tells you more or less where you are on the map. Here is that subduction zone. Volcanoes would be at the squiggly line. We're going to zoom into 50 million years ago. This darker line, that's the subduction zone. That's the convergent boundary where one plate is going down. Here are the volcanoes. And notice that our region is still ocean, and much of it would be deep ocean. 30 million years ago, here's that subduction zone. And notice it's a mix of land and ocean, but still mostly ocean for us. 20 million years ago, something has changed, because notice the subduction zone, that darker line doesn't go as far south. This is not subduction. That's the San Andreas. The San Andreas has formed, at least to the south of us, by 20 million years ago. And as we get to 15 million years ago, we can see that that San Andreas has eked its way northwestward a little bit more. And by 10 million years ago, somewhere between 15 and 10 million years ago, the San Andreas replaced the convergent boundary in our region. So it's a relatively recent thing. So how did that even happen? That means subduction convergent ended, the plate went all the way down. And then once that subduction was over, the San Andreas took over. So I will show you a video of it because it's much easier than arm waving. I want to point out here on this bottom left that in pink, it says captured part of North American plate. What's in pink is literally historically part of North America, but it is now being moved along the San Andreas. That will make more sense here in just a moment. So the San Andreas, its formation is the ending of convergence in the beginning of a transform boundary, literally a transition between tectonic boundaries. That transition from convergent to transform changes everything on our coastline. It leads to uplift. So all of our marine rocks that formed in the ocean, they get uplifted by this process. So you and I can walk on them today. And that uplift is going to be associated with the formation of mini faults, really millions, and the formation of mountains and valleys. And our region, when you see mountains and valleys, that means there's a fault between, or at least in proximity between mountain and valley. The only reason there's a mountain and a valley is because a fault has created a topographical difference. But we also got volcanoes out of the deal, and that's important because volcanoes produce different kinds of soil. So 30 million years ago, I'm in the bottom left. Here in yellow is our Pacific plate, oceanic. Here in blue is our Farallon plate, also oceanic. But here in red, that is our divergent boundary. When this divergent boundary in red meets the black line with the teeth on it, that black line with the teeth on it, that's the convergent boundary. The meeting of those two is the end of the subduction, the end of the Farallon plate going down. And notice by 20 million years ago, that had already started to happen. To our south, more in the LA region. And now when you have the Pacific plate touching the North American plate, it's now a transform boundary. It has replaced convergence. When we get to 10 million years ago, more of that Farallon plate, the northern piece we call the Juan de Fuca, the southern piece, the Cocos, more of it has completely subducted, and therefore the San Andreas is even longer. By about 15 to 10 million years ago, it makes it up to our region of the coast. And here at the present time, this is giving us a pretty good idea of our current tectonics. So I'm going to show the video in the upper right. And it's one of those videos where you could watch this a billion times and your brain would still have a hard time seeing what's going on. So here in the right side, this is in millions of years. So 40 million years ago, and it's going to, the white bar is going to move up to show you progress of time. The red line with teeth, that's the subduction zone. The red line without teeth, that's the divergent, the pull apart zone, creation of new plates. And when you see orange show up on the map, orange is going to be regions where the land has relaxed, stopped being squished. Convergence is all about squish, squish, squish. So when the convergence ends, the rocks themselves kind of just relax and spread out, and therefore North America can widen. So notice when the thin red line meets the red line with the teeth, that is the beginning of the San Andreas. Now we're going to watch a whole chunk of North America being pulled west and northwest, smearing the coastline. When I think of the San Andreas, when I think of a transform boundary, I think of a smear zone that quite literally our coastline is getting smeared northwestward. The faults of the transform boundary are what we call a right-lateral fault system, which is just a fancy way of saying that during an earthquake, if you were to look to the other side of the fault line, everything would appear to move to your right. It's just a which direction are things moving term. You can see, a second, look at that going again. You can see how our entire coastline has been shifting northwestward. The San Andreas just tends to be the focus of that shift, but really the entire coast range is shifting. That includes all of Sonoma and Marin counties. The rocks of the Salinian block that make up much of Point Reyes and Bodega Head, those rocks that formed at depth have been uplifted. They had to be faulted west and then northwest to get their current location. And based on the way rocks have moved relative to each other, we know that this process of San Andreas smearing has been taking place for about 30 million years. But that also means some of our rocks came from Southern California, and that's going to contribute more complexity to our soils. But that process of the convergence ending, remember that was fueling volcanoes further to our east over where the Sierra Nevadas are. That process of that convergence ending and being replaced by the San Andreas rent cracks and deep gouges into the crust, which allowed magma to rise to the surface. As the San Andreas formed, as it grew northward, there were gaps in the crust that allowed magma to come to the surface, and that's how our more recent tertiary volcanics made it to the surface. So I'm in the center bottom. Everything you see as triangles that are in dark purple, in red, and in this kind of magenta color. All of those are rocks that have erupted as a result of the formation of the San Andreas. The Sonoma Clear Lake volcanics, we can see that that's a fairly large amount of volcanic material. Notice here, I'm just put this map on here specifically to point out Mount Burdell, because the other half of Mount Burdell, notice there's a fault here that cuts that volcano in half. The other half of those volcanic rocks are much further to the south. They're South Bay because the fault has separated that volcano and broken it into two. You can see that faults are responsible for really shifting a lot of the rocks as we know them. So anytime one rock ends at a fault, you know that the other half of it is somewhere else. It's just moved to a different location. The Sonoma volcanics erupted largely, and these are very rounded numbers, largely between 12 to 3 million years ago. There's a huge variety of igneous rocks. Some of the rocks I have pictured here on the left. And the Clear Lake part, which is, of course, in Lake County, that region is still volcanically active because it's the most relatively recent part of the formation of the San Andreas. So there are still active volcanoes in Lake County, like Mount Konocti. Mount Konocti is a volcano. It will erupt someday. But these volcanic eruptions brought volcanic igneous rocks to the surface relatively recently, which have played a huge role in our soil development. Because when you look at maps of vineyards, most of our vineyards are actually on our volcanic rocks because those rocks produce the right chemistry to create andisols, which are a kind of soil that is just perfect for growing grapes. So when we think of Mount St. Helena, I've added this in because people ask me this question all the time. So if you were about to ask it, here's your answer. St. Helena is not a volcano. It is the remnants of a volcano. So this series of images on the right, this is actually Crater Lake. This is not St. Helena, but it's the best images I could find. Crater Lake was called Mount Mazama. It blew itself to smithereens. Quite literally, it emptied part of its magma chamber. The volcano itself fell into its own magma chamber, and the result is a lake. So if I were to take this same concept, when you go to Mount St. Helena, what I have kind of put in a box here on the bottom right, that is Mount St. Helena. It's a piece of the volcano, the collapsed volcano, that has since been uplifted by faulting. The faults are the reason it's a mountain, but it's made out of volcanic rocks from a past time of the volcano exploding and quite literally destroying itself. I do love volcanoes. Only mountains can destroy themselves like that. Now we have all these volcanoes erupting. That's absolutely going to play a huge role in soil formation. But we also need to consider that over the last 30 million years, as the San Andreas is forming, that there's also going to be huge changes to which parts of our region are covered by water, are part of the ocean, and which parts are land. And during the last 30 million years and ongoing today, the land is uplifting. The San Andreas has just enough of a squeeze factor to continue to lift the land up. So ocean rocks are being uplifted. Early on, until recent times, most of the uplift would have been taking those rocks out of the ocean, and only fairly recently have those rocks been part of the land you and I can walk on. And then rivers and rainwater take over, eroding that land and creating the landscape as we know it. And whenever we're talking about land that's eroding above sea level, we call that subaerial erosion. And that's what creates a lot of the shapes of the mountains that we see today. What I find amazing is that our Northern California river watersheds, like Sonoma County, Marin County, Russian River region, have only been rivers for this last 6 million years. And that's really recent. That means it has only been land to be walked upon for about the last 6 million years. There was never a dinosaur that walked next to the Russian River. There's too big of a gap in time. I should say, never a non-Mesozoic dinosaur. Dinosaurs went extinct 66 million years, except for the birds. The birds are dinosaurs. The Quaternary Ice Age, so between 2.58 here, this is the beginning of our current ice age. And many of my students know that my biggest pet peeve is when people say we're not in an ice age. We're in an ice age. We're just in an interglacial stage of an ice age. It's relatively warm right now, but the last 2.5 million years, that's the ice age that we are still within. Look at how much sea level has changed in that period of time, all the ups and downs. So that means there's times when what you and I call land is underwater, and times what you and I call the ocean is actually land. And I think the best example of that is in the bottom left. This is 18,000 years ago. This is the coastline. You can see the outline of the San Francisco Bay, and you can see the river systems because that was not a bay at that point. That was actually part of the land. Mammoths would have been walking through that, and they would have had to walk probably 30 miles further west to get to the ocean. You can see where the Farallons would have been as part of lands rather than islands. And when you compare this landscape to 5 million years ago, you can see how much of what was once ocean is now land, is part of our landscape. And as I come to the center top picture, everything in this kind of, I'll call that a mustardy orange color. That's relatively recent rocks that formed in the ocean. There's fossils in there, so that creates its own interesting soil that's definitely very good at forming grasslands. There's a lot of silica in it. So that's relatively recent marine rocks overall, as is a lot of the orange stuff through here and a lot of the yellow stuff through here. All of that is relatively recent. I debated as to whether or not to take out this slide, but honestly, I think everyone should know what used to live here, especially for plant people. When you think of what the plants would have been like during the colder times. I'm going to go back for a moment. Every single time you see the graph at a low point, that is a time when there's more ice on Earth, sea level is lower, overall climate is colder, and our region would have been significantly colder and wetter. It didn't have glaciers, but definitely much, much wetter. You can see what our coastline would have looked like. There's those Farallon Islands right through there. There's San Francisco. And everything we see in the light green would have been grasslands, completely different flora. Coastal plains, grassy valleys, there would have been lots of freshwater marshes. A large number of small lakes would have dotted the entire region, hosting lions and wolves and saber-toothed cats and bears and jaguars and mammoths and mastodons and horses native to North America. The horses we have today, they came from Europe. So these would have been genetically different. Camels and bison and llamas and tapir and moose. So many animals that we can barely imagine because the landscape was so different. And though we tend to be a little animal centric, we know that many of these animals would have been herbivores. And so they would have had a diet specific to the grasslands that were dominant in this region. Most of those plants do not exist in our region anymore. Climate change has changed our ecosystem, but there are some small pockets here and there where some bits of this Pleistocene epoch ecosystem still exists as like remnants of that plant world. There was a mass extinction at the end of the Pleistocene epoch, which is why these animals are not the dominant animals of our ecosystems today. Because for the last 11,700 years, our sea level has been rising. We are in an interglacial stage of the ongoing ice age. When there's no more ice on our poles, then the ice age is over. If that were to take place, if there's no more ice, then our sea levels will be 360 feet higher than they are now-ish. I mean, they've already risen this much since the last time of so much ice on Earth. We could have the sea levels go up that much higher. At the maximum, Bodega Head would be mostly underwater, but the very peak of Bodega Head would be an island. That's how much sea level could rise if the ice age were to end. And when you think of 25,000 years ago when sea level was relatively low, there was more ice on Earth. Notice how different our coastline would have looked. We would have had so much more land, probably a good 30 extra miles of coast overall. This series of maps here just shows you how our coastline changed from 20,000 years ago. The Farallon Islands were not islands, they were just mountain peaks. To 13,000 years ago, you can see that shoreline changing. To 12,000 years ago, now the Farallon Islands would have been partially islands. to 10,000 years ago, where the islands are islands, but still the coastline would have been relatively far to the west. As the sea level's been going up, of course, temperature has been going up, and our climate has changed from relatively wet to dry. So there is a natural climate trend in our region of drying that is being exacerbated and sped up by anthropogenic or human-caused climate change. So temperature goes up, coastline moves inland, islands form. At some point in the future, Point Reyes will be an island. Bodega Head will be an island, at which point there will be a change in the way that the ecosystem evolves. So I'm going to refocus here in on soil, because now we have an idea of the many processes that created our geologic complexity. Why do we have volcanic rocks and sedimentary rocks from the ocean and from rivers, and metamorphic rocks from great depth? Because there's this long geologic history. But what's on the surface? Because the surface rocks are going to determine the soil that forms. So I'm going to start on the right side on this cross section. So it's like, here we're looking at the top of the cake, and we're now looking at from the side, the inside of the cake. What are the layers at depth? This green color, that's the Franciscan Formation. Those are the rocks that got scraped off the ocean floor, off the Farallon plates, and are the basement rocks. And notice that that green is at the surface in some places, in which case that's going to play a role in the formation of soil there. The orange, the orange color here, that's Sonoma Volcanics. So you're going to get more volcanically derived soils there. So you'll have different vegetation in the volcanic regions. And the areas that are kind of this buff brown and this blue color, the Petaluma and Wilson Grove formations, those are all shallow ocean depositions. So that's the sedimentary sand and mud that was laid down during the end of the oceanic times in this area, as the land lifted up out of the ocean and the ocean receded, but also as sea level went down. So this is all oceanic rocks, and you can see a lot of that's at the surface. So that's going to form different kinds of soils as well. Notice that our Wilson Grove formation in this kind of buff color is more dominant in the west. It's this marigold orange color here. And therefore, our vegetation in that region is very different than what we see further to the east. So these would, if I'm simplifying, these would be our main three rock groups that are going to form different kinds of soil. So just to connect the two, the orange here is pink on this map. So here's Sonoma Mountain, here's Mount Burdell, all volcanic stuff. And then the buff color is this orangey color through here. The Petaluma in blue is largely buried, but there's pieces of it that kind of pop out in this, it's a sort of pink color. I'm not sure what to call that color. So there's some of our Petaluma formation also formed on the ocean floor. And then the gray stuff that makes up much of Marin County, as well as northern part of Sonoma County, that's the Franciscan Formation. And that's going to be the much older oceanic stuff. And there will be more serpentine within the Franciscan as well. So those parent rocks, Franciscan, the Wilson Grove, Petaluma, recent marine rocks, as well as our Sonoma volcanic rocks, those are the parent rocks. Those are the rocks that are going to break down on the surface, and those minerals are going to go into the formation of the soil. So when it comes to looking at what forms soil, there is a terrible acronym called CLORPT. I'm not making this one up. See, I didn't even make this diagram. It's a real thing, CLORPT. CL is for climate. O is for organisms. R is for relief or topography. P is for parent material, the rocks that are being broken down to form the soil. And then T is for time. Soil itself is going to be made out of the parent material rocks, plus new minerals that form specifically in soil. So there's some new mineral formation, plus water and air. And some soils, that's 50% of the soil is water and air, plus decayed organic matter. If there's no organic matter, it's not soil, it's just rock dirt at that point. And then, of course, our living plants and animals. When I think of soil and its relationship to vegetation, I consider that the soil and the vegetation are maturing together over time. That early immature soil, I'm in the bottom right, can't host as many types of vegetation because there's just not as much nutrition available. And that as that soil forms over time, more nutrients may be made available, which allows the vegetation to become more diverse. But some forms of rock just are never going to have the right chemistry to actually support a wide variety of plants. So if I go here to the center, serpentine oftentimes is not going to support a lot of vegetation. Certainly some plants have adapted to it. I know those who've spent a lot of time on Ring Mountain know some specifics about a cool lily there. Oftentimes the plants that grow in it are more stunted because there's just not the adequate nutrition. I think the same thing about limestone formation. Limestone oftentimes just supports grasslands. There's not as many types of plants that can become trees, just doesn't have quite the buffet of nutrients. But when I think of volcanic rocks are a smorgasbord of nutrition. They tend to get a lot of different kinds of plants. So when you have the rock breaking down to form the soil, that's called residual soil. That means the soil is going to be dependent on whatever rock is there in the first place. So that tends to be more of the mountains in our region. Now, some of the soil will wash down via the rivers and end up down in the valleys, where it's going to be a mix of the soils that came from the surrounding region as a result of gravity and water washing it down. And that's depositional soil. And depositional soil is just reworked soil, as in it didn't form particularly there, it usually forms elsewhere, but it tends to support a wider variety of plants because there's just more nutritional sources coming in. Residual soil oftentimes will have more specific plants that can actually live on it, specific to that rock chemistry. And for those who love soil, I wanted to, just in case you weren't already aware of it, tell you about Web Soil Survey. It's been a while since I've been on the website, but it's not a great website. Like, yeah, trying to instruct students on how to use the website takes an entire class in and of itself. It's not really all that easy to navigate, but it's a great website when you get into it because you can zoom into an area and you can actually look at the soil in a specific location. It will tell you about climatic factors associated with that soil. It will also give you an idea of some of the rock components of it. For example, is there a lot of clay? Is it going to shrink and is it going to swell? But you can learn a lot about the soil through a web soil survey, which can also then give you an idea of what kind of vegetation is present. So if you're hunting a specific plant and you know you found it in location A, you can figure out what that soil is and then use web soil survey to find where else can I find the same kind of soil where that plant is more likely to live. And then when we look at the soils of our region, we go, yeah, that's geologic complexity has created a lot of soil complexity. So in the upper right, we have the State Soil Geographic Database, where each color is a different kind or specifically order of soil. I believe there's 12 orders of soil associated with, I think it's the USDA, did a lot of the original classification. And you can see them here in the bottom left, and Sol is for soil. And I put X's through the soils that we do not have in our region. Not surprisingly, we do not have permafrost. We also are not in the tropics. And we don't have the spodosol, or this requires cooler weather, but we have all the other kinds of soils in our area. You can see they are color coded. I'm going to focus a little bit on the andesol here, which is in this kind of green color. So there's some of that through there. Iridosols tend to be a little bit drier, so they are going to support plants that can deal with more droughty conditions. The brown mollisols, those are kind of like our bread basket soils. They like much of the Midwest is mollisol. We have quite a bit of the vertisols here, and those tend to have a lot of shrinking and swelling. So they tend to crack in the summertime as a result of shrinking so much. But each of these soils has different characteristics. They're going to have different nutrition. So notice that our andesols tend to be volcanic. They're named for the Andes, being volcanoes. The alpha sols oftentimes are going to be derived from volcanics. They have a lot of clay in them, and clay is good at holding onto water for some period of time. But the variety of rocks that we have in our area, that variety of plant materials, which directly is the result of our geologic history, plus the relief, which is the result of ongoing faulting, which is part of the San Andreas fault system, plus our unique microclimate variability, means we have a wide variety of microclimates and a wide variety of soils, and therefore the opportunity for many kinds of plants to exist. When it comes to looking at horizons, or the layering effect within soils, that is something that occurs over time. Clorped, unique climate, organisms, relief, parent materials, and time. But we can actually determine the age of soils by looking at their horizons. And that can give us a sense of how long that landscape has been evolving, which can help us figure out when did sea level drop and make that part of our continent rather than being underwater. But as we go through relatively rapid climate change times, we expect that as our climate changes, our plants are going to have to adapt relatively quickly, as are we, because we know that our summer maximum temperatures, I'm in the top left of the screen, they're getting higher. Our winter minimum temperatures are also changing, which we don't get quite so many cold spells. Our overall precipitation is changing. There are some forecasts that will suggest some of our area will get more rain, and others that suggest less. It's not entirely sure. But we do expect at least seasonal water deficits, which of course will have a negative effect on many plants overall. The vegetation, which is the result of the soil, which includes an aspect of climate and geologic history, the vegetation will evolve over the course of time. And when we think of what the vegetation was like during the time of the mammoths, we know that this ongoing evolution will continue into our future. So when it comes to those very rare plants, where might you find them? In the left side, we have Conservation Lands Network. And I did include a couple websites here for those who are like, where did she get those maps? The database.org and Bay Area Lands are where I got them. And what I found so fascinating here, I'm in the left side, is rank 1 rare vegetation, these areas. Notice that they kind of form in these kind of elongated strips of land in the northwest southeast direction, because the soil that allows for the rare vegetation formed because of the geologic features there. And of course, our geology has this trend of northwest southeast. And you can see that even in the way that rare plants are found overall. So when it comes to our landscape evolution, we find these islands of soil, relatively rare soils that can support relatively rare plants. That is the result of our geologic history, which there's a lot to that history. I went over it pretty quickly. Is also the result of the relief being our valleys and mountains that are because of the faulting associated with ongoing tectonics, the San Andreas, and of course, our microclimate variability, which is uniquely variable in this region. Because I know people who are 2 miles away from me who get very different weather than I do. And in the San Francisco Bay Area, our spectacular landscape is the result of ongoing evolution of climates, ongoing evolution of geology. The land is continuing to rise geologically. The faults are continuing to slide. That's not going to stop anytime soon. Sea level is continuing to increase. The climate is continuing to get a little drier with the potential of more discrete precipitation events. So the soil is going to evolve to reflect those changes in our environment. And the plants will also adapt. And we just live in such a spectacular area where you can actually go on hikes to see things like this. So I'm going to start looking at the chat here in a moment to answer some of the questions, but I do have a website, appreciatingearth.com, and I have a newsletter. I know I haven't done one in a while, but I promise I will soon. Please feel free to sign up for my newsletter if you want to know of when I'm doing walks and talks, etc. I'm just looking really quickly. Okay, so Rob asked, serpentine is created in divergent zones. Can I talk more about that? So serpentinites is a group of rocks that are made out of serpentine minerals. And serpentine minerals essentially are baked by hot water. Think of it as the rock being poached. And most of the time, but certainly not all the time, one of the main rocks that gets baked by the hot water is basalt, the same stuff that's erupting out of Hawaii, the dark black igneous rock. And when that rock gets hot, like way hotter than boiling point, hot water going through it, it quite literally changes the minerals due to the high temperature, and those minerals metamorph into serpentines. So there are plenty of serpentines that form at divergent boundaries. Some of those have certainly become part of our landscape because that divergent boundary is where the oceanic plate is forming, and chunks of the oceanic plate are part of the Franciscan. But you can also get that really high temperature of water baking the plate, that same oceanic basalt plate, as it goes down. As it goes down through subduction, it will get hotter, and that will cause that heated water to bake the surrounding rocks, forming that much more serpentine. So yes, serpentinite is going to be associated with high temperature and pressures in subduction zones, but the divergent zones also have high enough temperatures, pressures are lower, but high enough temperatures to also do serpentinization. Paul, I'm not sure which graphic you're referring to. Can we see the graphic in the lower right corner when the speaker refers to these?
A later message explains
No.
how to reveal that.
There
Press
we
the
go.
minus button at the upper right of the speaker box.
Okay.
And yes, the talk is being recorded and will be posted on our YouTube channel, probably in a couple of days.
So Carolyn asked about where to find remnant plant communities from the Pleistocene. I think plant people are probably going to be much better at like identifying these, but I would, for example, this is a geologic map thing. Okay. So we saw some of the colorful maps. On those colorful maps, when I see the symbol QPA, I know that means that during the Pleistocene, that was wet. So it was a marsh or a pond or a lake at that point. Those now have, for the most part, dried up and become meadows. So for example, there's some in Annandale State Park. those are the regions where I would probably look for some of those more like Pleistocene remnants, some of those plants that would have evolved during the Pleistocene, but have continued to evolve and adapt to survive today. But QPA on a geologic map is where I would look for that. And then I would ask one of you to come identify the plants for me. Let's see. How do freshwater springs, how do freshwater springs play into this? So a spring is really just where you have groundwater leaving the ground and going onto the surface. So it is the result of groundwater becoming surface water. So you're going to have that become part of the process of breaking down the rocks of the surface to form soil. So this makes me think of Sonoma Mountain in the Fairfield Osborne Preserve that's part of Sonoma State, because there's a spring that drains into a marsh, and that marsh has completely different soil and plants than all of the land around the marsh. This spring played a really big role in creating that wetter environment and a completely different soil to support those marshy plants. And yes, you do have an abundance of water in the Inverness area. Serpentine rocks tend to be higher in magnesium. That is true. Yes, this is a lot of what you do see at Ring Mountain, but it also tends to have quite a bit of things like chromium in it, which is not great for many plants. Again, some of you would probably be able to state this better, but from what I understand, there is a plant, I think it was a lily, that has evolved to quite literally take the chromium out of the soil, put it in its leaves as it's growing, and then drop the leaves. So it's basically created a relatively chromium deficient region around its roots. And then that soil allows it to go through its next life stage, because it's pretty toxic for plants. So some plants have quite literally evolved to rid itself of that toxicity in order for it to survive, which I find fascinating. Robert asks, is there an explanation for why the east side of Mount Tam is so much steeper than the western side? Yes, that's actually not too uncommon in this area. There's certainly exceptions to it, but it's the way the faults have formed that tend to, I don't know if my hand waving can actually do the job here. So it tends to lift one side of the mountain up at a higher angle. So we tend to have steeper sides on the east side and a little bit more gentle slope on the west side. Is just part of the mechanisms of the way the San Andreas fault system works. And Mount Tam, as well as Mount Diablo, those two mountains are relatively high points on our landscape because there's a convergence of faults that makes it a pinch point. So as a result of there being just enough energy causing higher uplift, it ends up as a more prominent mountain. But the east side being steep is just part of the way the faulting occurs, more like this. And I'm doing more of an arm waving thing here versus it just lifting straight up. It's just differential lifting. I hope that was in any way clear. Yeah, it was.
Rob, go ahead.
Yeah, thank you for answering my question about serpentine formation.
Yeah.
I see blue schist and serpentine on Ring Mountain, and I'm sure blue schist exists someplace else. Can you tell me what the difference is? Because I was told that blue schist forms under cooler temperatures, but the same high pressure. Is that accurate?
Yes, so blue schist is my favorite rock. So thank you for letting me talk about blue schist.
Yeah, mine too.
It's so pretty. So blue schist, there's a diagram called a metamorphic facies diagram. It's FACIES if you wanted to go online and look at a graph. Essentially, it's a graph that says at this range of temperatures and this range of pressures, this kind of rock facies will form. So blue schist is a facies of rocks. It's really a compilation of minerals that can only form at very high pressures, a subduction convergence zone, but relatively low temperatures. The temperatures will catch up, but at first during subduction, it's more about the squish, squish, squish pressure. The temperature follows later. So blue schist only forms in subduction zones as a result of the high pressure. If that plate goes down further and the temperatures get higher, then the rock eclogite forms. And you can also see eclogite at Green Mountain. It's on the north side, the trail that was up the north side, you can see it. So we're not surprised that eclogite and blue schist are found nearby each other because they really are part of the process of subduction. It's the only way they can form. A number of studies have been done to try to understand the relationship between serpentine and blue schist. And serpentine, I'm going to try to get this right for David Barrow because he will be mad if I get it wrong. He's the one who did the geologic mapping of Ring Mountain and Tiburon Peninsula. So essentially, the blocks of blue schist and eclogite, which had to form at great depth, they had to obduct rather than subduct. They had to abduct to get back to the surface because they formed at great depth and they're now on the surface. It is hypothesized that the process, that the serpentine, which is relatively slippery and low in density, that it's what actually carries those blocks of deep rocks up to the surface and acts almost like a lubricant. So I think of it as like chunks of rock that are being uplifted along faults, but the serpentine is kind of paving the way for that, carrying the rocks with it. But the truth is we don't really know for sure. The studies are, of course, being done, but geologists like to disagree with each other. And there are many opinions.
So, may I ask you one more question?
Yeah.
So can you spell the name of that other mineral you said?
Eclodite.
Eclogite. It's ECOLI. Eclo. Helps when I write things down. Eclogite. ECLOGITE.
Okay. And how does it difference in appearance than blue schist so I could identify it?
Yes. So blue schist is going to have more of the blue minerals, including a mineral which goes by the name glaucophane.
I know that.
That one. Whereas eclogite tends to be green and red, sometimes a little bit of white because it has different minerals. The green is oftentimes a pyroxene. The red is garnet. You can find garnet in blue schist as well.
Yeah.
But if you know the north side of Ring Mountain, where you're starting off near sea level and hiking up the north side,
Right.
there's a giant rock that everyone has to kind of squeeze through. Like it's on your left side as you're heading up. That's mostly eclogite.
Okay.
And then Turtle Rock is mostly blue schist.
Oh, yeah, right. It's a beautiful rock.
So pretty.
Yeah. Well, thank you for all the details.
You're quite welcome. See if there's any other questions. Jean asked, am I teaching somewhere this fall and in the spring? Things are very much in flux. I will definitely be doing a few walks and talks, which I will announce via my website and newsletter. Otherwise, I don't know. Sonoma State is very much in flux, and therefore my career future is as well. I'm very excited to know what I will be doing because I don't know.
Well, we wish you all the best. This was an absolutely wonderful presentation, and I think we'll all want to go back to the recording of it to pick up some of the details we might have missed.
It could use probably a few watches to get more of the details.
Yeah, and quite a few people came in late, and so I encourage you to go to our YouTube channel in a few days to look at this again. And so thank you again. And next month, still working on it, but could well be a program on restoration work in Homestead Valley area of Mill Valley by Maribeth Graham, who has been instrumental in spearheading a lot of work that's taken place up there. So thank you all for joining and hope to see you next month.
And thank you so much for having me. I always love doing these things.
Great. So happy to have you. Thank you. Good night, everyone.
Good night.